Welcome back to ECE 441A 541A. Earlier in class we were taking this matching quiz, and I thought I should probably at least give you the answers, or at least share with you that you were or were not getting the right results in comparing the S-domain pole locations with the time response trajectories, where we're now looking at two different plants or two different sets of poles and their corresponding responses, let's say on the left plane that we're viewing here with the step response. For the first particular set of poles, let me just be a little bit more explicit with which pole is which. With respect to pole A, that's the green pole on top, or it's the lowest pole in the bottom in the negative or in the third quadrant of the complex S-plane. If we look at this, both of those poles or sets of poles are the same distance into the left half plane, meaning they both have the same settling time. And if we go over to the diagram, they both seem to be settling at about the same location as far as our 2% settling time. And we could actually compute that if we wanted to from what we've now learned about settling time behavior. We now can see that the settling time for both A and B, in terms of the pole locations, those both are into the left half plane a distance of 1. 4 time constants then will be the same as 4 over sigma. Sigma in this case is 1, and so we actually should be expecting a 2% settling time of 4 seconds. And in fact, that's when they both seem to enter the same 2% tube. We can't then distinguish between these two sets of poles based on settling time. How they are different, though, are they are different distances away from the real axis. If we draw a horizontal line from those pole locations to the j omega axis, this bottom pole, or set B, or plant B, has a damped frequency of 1, and plant 2, or plant A, has a damped frequency of 2. We can now use that information to help us learn a little bit more about the quickness of the peak, and we actually should be expecting, if we look at our peak time for, let's say, point A, the time to peak, we have learned, is now 4, or pi over omega d. For point A, we can see that omega sub d is 2, and we should be expecting a peak time of about a half of pi, or 1.57. And if we look at 1.57, that's now intersecting with curve number 2. So now in that case, it's sort of indicating that we need to match up point A, or pole pattern A, with transient performance 2. And if we look at that relative to this particular result, then it looks like our answer would be A2, B1, or item number 2. We can maybe try to correlate that a little bit more, or get another piece of information about those two responses if we actually look at their percent overshoot. If we look at the percent overshoot, let's say of point B, if we examine its pole locations, point B is actually at -1 plus J1, or that now has an angle of 45 degrees. Or if we now wanted to find the damping ratio, we now have the cosine of 45 degrees is 0.707. And if we look at figure 5.8 in the textbook, and we now find a damping ratio of 0.7, that now corresponds approximately to a 5% overshoot. So now the percent overshoot for point B should be about 5%. If we go back to this diagram, we see that response number 2 has about a 20% overshoot, and point B, or I'm sorry, time response 1 has a percent overshoot of about 5%, and that says then that B1 is connected, or pole pattern B is connected with response number 1. And we can then see then that we've concluded that the correct answer for question number 1 is to pair up pole pattern A with response 2 and pole pattern B with response 1. That's the answer to question number 1. If we now look at question number 2, now if we look at this, we actually see that both of those pole sets, and in this case, A, let me label it, A is the front or the pole pattern that is closest to the imaginary axis, but both of these poles have the same imaginary component, which says really that those two pole pairs are going to have the same peak time. And if we were trying to find the peak time and compare those, we wouldn't really be able to get any distinguishing information by looking at the peak time. And in this case, one of these curves doesn't really even peak, and so we can't even compare the peak time. But if we looked at the blue curve, then that is picture number 1. Maybe I should go with the blue color. I'm sure I'm not being consistent with this, but on trajectory number 1, if we wanted to sort of look at its time to peak, that now looks more like the time to peak is now pi over omega sub d, and it almost looks like that's time to peak is roughly about pi, and if we now solve that for omega sub d, we get omega sub d of 1, and that's actually what our imaginary component is for trajectory number 1, or for pole pattern A and for pole pattern B. If we look at these two, we can't really distinguish anything from their peak time, but they do have a different distance into the left half plane, and pole pattern B will actually have a faster settling time, just because it's further into the left half plane. We can also, and if we look at the settling time for, let's say, pole pattern B, time to settle is now 4 tau, which is 4 over sigma. Sigma for the B poles is actually 2, so we would expect a settling time of about 2 seconds for the B pole. We come over here, and in fact, one of these does look like it's settling at 2, which is pattern number 2, or response number 2. So this says that B2 is how we would compare or match up the poles with the response. If we looked at these two poles, we know the peak time can't differentiate between those. We have found a way to differentiate between them using the settling time. We can also examine their angle with respect to the origin, and in fact pole pattern B has a smaller angle, and we would anticipate that having less of an overshoot. And which of these responses has less of an overshoot is response number 2. Again, then the percent overshoot behavior would seem to match B with response 2. If we look at A, pole A, it now has poles at -1, plus and minus J1. The angle theta for that is now 45 degrees. If we find zeta from that angle, we now see that that gives us a zeta value of about 0.7, and we've already seen that for a zeta value of 0.7, that corresponds from figure 5.8 to a value of 5%. And so A, poles, we would expect those to present a percent overshoot of about 5%. Response number 2 doesn't even give us any overshoot. Response 1 does. So this particular result on percent overshoot would seem to pair up pole pattern A with response trajectory number 1. And so now we're looking at B2A1 for the answer for question 2. And that's now response 1 for question number 2. Finally, if we look at question number 3, again, if we try to compare or maybe more effectively identify which point is where, the first set that I've now highlighted in class in blue will say that's pole pattern A, and the second pole pattern is B. Now they do not line up vertically, they do not line up horizontally, and they do not have the same angle. So we should actually be able to use sort of all 3 of our design specification relationships to differentiate these poles from the responses on the left. If we look at A and the angle associated with A, the angle of the poles for A it's bigger, and so we would expect more percent overshoot from the poles relative to A, which would seem to say that this green would be A because of the percent overshoot relationship. If we looked at that, now A is at -1 plus J2, we could find the angle theta from that. That's now the angle that had a tangent of 2 over 1. If you look at the inverse tangent of 2, that's now 63 degrees. If we now compute the cosine of theta to obtain the zeta value for pole pattern A, now the cosine of 63 degrees is approximately 0.45. Or we could go over to the response and say response curve number 2 has a percent overshoot of approximately 20%. A percent overshoot of 20% over here on our figure 5.7, we would now say, oh, we need to go over to this curve that's giving us our percent overshoot zeta relationship, find where that now intersects 20 and go down, and it looks like we would have a zeta value of about 0.45. So this now says we have a zeta value of about 0.45. Those two agree, and so we now can look at, from a more quantitative perspective, associate pole pattern A with response trajectory number 2. So now we have this A correlated or matched with response number 2. If we looked at the settling time, because both of these have different settling time characteristics based on these two sets of pole pairs are actually at two different distances into the complex S-plane, left half S-plane. If we look at pole pattern A, which is closer to the imaginary axis, it has a real part of 1. Our settling time, 2% settling time, is now 4 tau, which is 4 over sigma, or with a real part of 1, we now would expect 4 seconds for A. If we go back here and look at A, or I'm sorry, to try to find some response that's settling in 4 seconds, that looks like it's more number 2. So again, this would seem to indicate that A was matched up with 2. If we look at the other settling time, point B, its settling time is 4 tau, but B is further into the left half plane. It's a distance of 2 into the left half plane, so we would expect the response associated with pole pattern B to be having a settling time of about 2 seconds, and in fact that's what it does. And so that's now saying that the blue response, which is response number 1, looks more like B's poles, so this is now saying we have B1 based on settling time. We could also look at the peak time, and over here it's hard to find a peak for response number 1, but for response number 2, which is the green, we can now see that for that particular response, which was response number 2, we can find that the time to peak, which is pi over omega sub d, is approximately, let's say if we read that off right, that's about 1.57, anticipating what that probably should be. Well, that's just pi over 2, which is saying that omega sub d, based on the time response, would correspond to complex poles that have an omega sub d of 2. We come over here, and omega sub d of 2 corresponds to A, and so now this says that we can actually match up A's pole pattern with response number 2. And in fact, B really doesn't have much of a response because its angle is less than 45 degrees. And so if you go back here and look at zeta values bigger than 0.7, it's hard to see much of a percent overshoot for zeta values of 0.7 and beyond. Meaning the answer to question number 3 is going to be A2 and hopefully B1. So this is now A2 and B1, or response number 2 for that particular question. And that should then give us the answers to our quiz.